This video will deal with the Poisson probability distribution. The Poisson distribution is like the binomial distribution in that it's a discrete probability distribution. That is, it can only take on the values 0, 1, 2, 3, 4, etc. But unlike the binomial and the Poisson distribution, you can have up to theoretically an infinite number of outcomes. The binomial distribution, the maximum number of outcomes is n, the number of trials. So if you're going to do 10 tosses of a coin in the binomial, the maximum number of heads is 10, not infinite. Okay. The Poisson distribution is infinity, as you'll see in a bit why that is true, or why it can be true. But in a lot of other respects, they're similar. Okay. Basically, we're talking about x being occurrences of some event over a continuum, something that's continuous. And the best example we have of a continuum is time. Another one, of course, is space. Both of those time and space can be divided up into infinitesimally small periods. Okay. So that's very different than a binomial, but now we're talking about occurrences. And the Poisson distribution is used to great benefit in a subject that some of you might take. It's called either management science or operations research, and it's the mathematical procedures that enable people who deal with random occurrences to optimize their process. Okay. For instance, how many checkout counters do you need open in a supermarket at any particular one point in time? Now clearly they change that as they need to, but they have in mind a certain number of cashiers, checkout people that they need. Same with bag people. All right, or same thing as now getting the old days, but still done. Telephones. All right, how many telephone operators do you need to help out at the main switchboard at UAB? That type of thing. All right. The Poisson distribution has only one parameter, and that is its average. Okay, as soon as you are told the average of a particular Poisson distribution, then you know exactly where to go to calculate probabilities, and we all have probability tables just like we had for the binomial. In contrast, the binomial has two parameters. The number of trials and the probability of success on one trial. Okay. Let's have a look at the Poisson tables, and you'll find that they are very similar to that, the similar look as that of the binomial. Okay. All right. So this is the Poisson tables. It's the first panel for that. Sorry, it's not the first panel. First panel's up here. And just like the binomial, this is a cumulative distribution. Sorry. Alright, so it gives you the probability of x less than or equal to some number a. Those numbers a are down the left hand side. The values across the top, the 0.1, the 0.2, 3, 4, well, etc., and that scrolls over. Alright, the top one stops at 1.5, then goes 2, 2.5, 3, etc., and 7 there, and then it keeps on scrolling to 7.5 through 20, and then it stops. Alright, those are averages, average number of occurrences for a particular time period. So let's look at a very simple example. Let's say that phone calls arrive at an office at a rate of one, that's an average rate of one every 5 minutes. Alright, like I said, that's an average rate, and we all know that it's not going to be every 5 minutes that they're going to get a phone call. And we could answer the probability like, what is the probability of getting at most 2 calls in a 5-minute period, any 5-minute period. Okay, so this is the probability. X is the number of phone calls, at most 2. Alright, you read those the same way as you did for the binomial, because this is just another discrete probability distribution. So X less or equal to 2, given certain parameters. So as before, the binomial we had 2 parameters, the n and p. In this case, we'll just have an average, and we'll just write it average. Some textbooks give it a symbol, and those symbols actually make life difficult in this case. Alright, so this is 2 in a 5-minute period, probability thereof. Then we need to know the average rate in a 5-minute period. Well, the average rate is 1 in a 5-minute period. So you make sure that the number of occurrences and the average are for the same period. Okay. Alright, that's simple enough. We just go to our Poisson table and read that off. Okay. X less than 2. Alright, less than or equal to 2. An average of 1 is just there in the table. Alright, so that number is 0.920. Alright, so it's about a 92% chance of getting 0, 1, or 2 calls in a 5-minute period. That's pretty high. It's the probability of getting more than 1 in a 5-minute period, or in more than 1. The statement does not include 1. Alright. 5-minute period, the average number of occurrences is still the same as 1. Alright, so we're looking for not 1 occurrence, but 2, 3, 4, etc. through infinity. Okay, so this is what we're looking for. Alright, the rest of the probability distribution is 0 and 1, so we're going to take everything, which is 1, minus, and then subtract out 0 or 1 occurrence. Alright, x less or equal to 1, average equal to 1. So this works just like the binomial, and it should, because it's just another discrete probability distribution. So we need to go to our tables, average of 1, less or equal to 1. Okay, and that's this value here, 0.736. So to the answer to our question is 0.264, I believe. Okay. Alright, now let's look at this problem. And at any point through here, since I believe these problems are relatively simple, you should pause the video, try to do the problem yourself, and see what my answers are, and then compare them, of course.